is Dr. Didong, and he got his PhD degree from Duke, and now he's assistant professor in biostatistics at the UNC, and he has training on applied mathematics, and he found a job at Biostat, and we often meet each other at the machine learning conference. And here's another fun fact. So if you go to his website, you can look at his Chinese name. Okay? So my name, I can feel when people say my name, they try to be careful not to go wrong. Okay? But his name is easy to say in English, but if you look at his website, I'm from China. I cannot read his name. I cannot write it. Anyway, so he's doing a lot of cool stuff. Sorry, doing applied geometry on the brain network, and today he's going to talk about network curvature.
Thanks, Gordon, for the introduction and the invitation. This fun fact is surprising to me, and I'm not prepared. Actually, another fun fact. Till now, only 2 people know my name. Went back to China. My Chinese teacher in high school doesn't know my name. So it's a very rare character. So since this is like a flash talk, I won't make very technical stuff here. So instead, I will give an overview of a field called network curvature, which might be less well known in certain communities than others.
No, it's not working.
It doesn't work?
Yeah.
Okay, so I can stay here. I guess since you are here, I don't need to convince you, network data is everywhere. For example, we have this brain connectivity network, I can skip it. There are a lot of popular tools to analyze network data depending on your background, your expertise, or your interest. You can find different fields everywhere. And I'd like to thank Tom to advocate for geometry. It's not like that well known compared to some other method like a machine learning method or statistics if you are from a stats or biostat department. And so geometry, in my point of view, is pretty cool. It has been really powerful. It's one of the pillars in math in the past 2,000 years. So when people mention geometry, usually we refer to this key concept called Gauss curvature, which really is an intrinsic measure of curvature. It depends only on the distance within the space. It doesn't depend on how this manifold is embedded in Euclidean space. That's why we call this intrinsic. And so when people mention Gauss curvature, I always have these 3 examples. If you look at a sphere, it has positive constant Gauss curvature. And the middle one is a cylinder, is flat, so it has 0 curvature. Or if you look at a hyperbolic space, it has a negative curvature. The concept I would like to discuss today is a little bit more technical. It's called Ricci curvature. So it also measures how the space is different from Euclidean space in some sense. And there are 2 very, very famous successful applications with Ricci curvature. One is in relativity, when Einstein proposed this field equation. The other one is more recent. There's a famous conjecture called the Poincare conjecture. Was proved about 20 years ago. The key technique is Ricci flow, which is closely related to Ricci curvature. This is beautiful, this is powerful, but so what? Why we care about this? These curvatures are well defined on smooth surfaces, but we deal with network or graph, which is discrete. And the natural question is, how can we define such curvature on the discrete space? So that's the natural question. Can we define Ricci curvature or any type of curvature on networks? This is a very challenging problem, but fortunately, some smart people solved this problem already. For example, in this paper published in 2009 on Journal of Functional Analysis, Olivier proposed a network that is well defined on any metric space. So imagine you have a network, you have a natural graph distance, and so which is essentially a metric space. So it's a special case of this. So that means the Ricci curvature is really well defined on networks. So to honor Olivier and this milestone paper, nowadays we call this curvature Olivier-Ricci curvature. Olivier for him and Ricci for Ricci curvature. And so why we care about Ricci curvature, how can we apply Ricci curvature in network analysis? So here I would like to discuss 4 applications. The first one is community detection. So here is a toy example. We have a small network, and clearly we can see 2 different communities. So now we calculate the curvature of each edge, colored by the curvature value. we can see if the edge connect two different communities, it's in purple, means that the curvature is negative, it's very small. Well, if the edge is connecting two nodes, the same community, the curvature is positive, is in green. So motivated by this simple observation, or you can make a histogram, you can easily detect whether the edge connect different communities or the same community by looking at the curvature. So there are some existing work to propose new community detection method based on this Olivier-Ritchie curvature. Another application is really on the visualization side. Here's an example of the router network. And here we can see red color means negative curvature, blue means positive curvature. So clearly, if you want to subsample from this node, you want to preserve the overall shape, you better keep the red edges, which is really the so-called backbone in the network. So this says, okay, if you want to preserve the overall structure, just keep the negative curvature edges. You can drop all the positive curvature edges. Another example was in medical study where they look at a huge data set with different cancer networks. And the question is, so if you look at healthy people and cancer patients, what's the overall difference between these two groups of people in terms of the network curvature? Okay, so they look at 6 data sets, and they calculate the average curvature of each network. They found that the average curvature for cancer people is bigger than non-cancer people. And the difference is summarized in the first row, and the p-value is surprisingly small. It's less than 10 to the negative 25. So there are some heuristic interpretation. Maybe if there's a cancer, the genes or proteins are more activated. It's more like a fully connected network, so the curvature is much bigger. That's the interpretation. And the last one is in deep learning. There's a field called graph neural network, which relies on graphs. On the left, we can see 3 different types of graphs. The first one is more like a fully connected, the curvature is positive. The middle one is more flat, the curvature is 0. And the last one is more like there's a bottleneck, so the curvature is negative. And in graph neural network, computationally, there are 2 issues. One is called over-smoothing, which basically means the weights of all the nodes are equal to each other. There's no information, really. Another one is called over-squashing or bottleneck problem. So here we can see 2 bottlenecks in red, and this will prevent the message passing. And so the author observed that, okay, every time you see over-smoothing, the curvature is very positive. Every time you see over-squashing, the curvature is very negative. Then when you train the neural network, you just keep track of the curvature. If you observe a super huge curvature, you just remove some edges. If you observe a very small curvature, you just add some edges. So this will improve the network architecture. Okay, so here we have 4 sort of exciting applications, and the question is this Olivier-Ritchie curvature perfect? And actually, there are some problems. For example, Olivier-Ritchie curvature involves the Wasserstein distance, which is computationally expensive. It's cubic in the number of nodes. And also, it's well suited for the so-called community detection problems, but not really suited for like protein or gene expression or brain connectivity analysis. So motivated by this, we propose a new curvature called lower Ritchie curvature. You can tell from the name, it's actually a lower bound of Olivier-Ritchie curvature, and it's very simple to calculate. I'll skip the technical equation, but it's really simple. You can look at the definition. And the computational cost is linear. It's instead of cubic for Olivier-Ritchie. So it's ready to analyze large-scale networks. And we do have some theoretical support. This is not from like nowhere. We can analyze this new curvature from the theoretical end. So I guess that's it. Today we introduce a new field called network curvature. We mainly focus on a representative called Olivier-Ritchie, and actually in this field there are quite a few different curvatures. So for edge curvature, we have like a Foreman, balanced Foreman, and if you would like to calculate curvature for each node, there are some other curvatures. So, and these are also well defined for directed network, like hypergraph. So there's an entire field on this. Future work, of course, we are actually working on this, collaborating with Goran on this. We want to apply this curvature to some brain connectivity. At the end, I'd like to thank my student Christine, who's leading this project. That's all for my talk. Thanks.